This might look like a math lesson, but really it's about something we all do every single day, organizing stuff. In fact, what if I told you that the way you store your laundry uses the exact same core logic that powers a ton of advanced computer science? Sounds kind of crazy, right? Well, let's dive in and see how. Seriously, think about it. When you've got a pile of clean laundry, you don't just shove it all into one big drawer, do you? Of course not. You've got your pile for shirts, your pile for pants, another one for socks. You're naturally, instinctively creating order out of that chaotic laundry basket mess. And believe it or not, that simple act of sorting is exactly what mathematicians do. They just give it a slightly more official name. They call it a set. And really, at its heart, that's all a set is. It's just a collection of things you've grouped together based on some kind of specific rule. Okay, so what's the big difference between just a random pile of things and a real, official, mathematical set? Well, it all boils down to one super important rule. And here it is, the golden rule. A set has to be well-defined. Now, that sounds a little technical, but all it really means is that you have to be able to tell with 100% certainty whether something belongs in that group or not. There's no gray area, no maybe, and definitely no opinions allowed.
Let me show you what I mean. If I said the collection of tall students, is that a set? No, because what's tall to me might not be tall to you. It's subjective. But if I say the collection of students taller than 150 centimeters, now we're talking. That's a crystal clear rule. You're either in or you're out. Same thing with expensive cars. That's just an opinion. But the collection of whole numbers between 3 and 8, that's a perfect, well-defined set.
And when we write these down, we have a specific way of doing it. We usually give the set a name, just a capital letter like A, and then we list everything that's inside it between these little curly braces. And all the things inside, we call those the elements of the set. There's even a kind of secret code to talk about what belongs in a set. See that first symbol? It just means is an element of. So if our set A is 1, 2, 3, we can write 2 is an element of A. And the other symbol, the one with the line through it, you probably guessed it. It means is not an element of. So 5 isn't in our group, so we write 5 is not an element of A. It's just a quick shorthand for what's in and what's out. Okay, so we know what a set is and how to write one. What's the next logical question you'd ask? Well, probably how many things are in it, right? And of course, math has a special word for that. It's called cardinality. I know it sounds a little fancy, but it literally just means the number of elements in the set. And we write it like this: n for number, and then the set's name in parentheses. So n of A is just the number of things in set A. Let's try a super quick one. We've got a set B, and its elements are red, yellow, and blue. So what's the cardinality? How many things are in there? 3. You got it. Red, yellow, blue. That's 3 distinct elements. So we'd write it out as n of B equals 3. See? Simple. But here's a fun little twist. What happens if you make a group with a perfectly good rule, but it turns out nothing actually belongs in it? For example, what about the set of all elephants that can fly? I mean, the rule is totally well-defined, right? We can check every single elephant on Earth and know for a fact whether it can fly. The thing is, none of them can. So what's in our collection? What does that set even look like? It looks, well, empty. And that's exactly what we call it, the empty set. Sometimes you'll hear it called the null set. It's a real, perfectly valid set. It just so happens to have nothing in it. You can write it with that circle with a slash through it, or just a pair of empty curly braces. And its cardinality? Well, obviously, it's 0. All right, you've totally got the basics down. So now let's get into a couple of pro tips for sets. These are the 2 big rules that make them so incredibly powerful and clean for organizing information. Rule number 1, sets hate duplicates. They only care about unique items. So if you have a list with the same thing written twice, the set just ignores it. It only counts it once. So if you start with this messy list, A, C, R, C, the actual set is just the clean, simple version, A, C, R. And rule number 2 is a big one. Order doesn't matter at all. A set is like a bag of things, not a specific lineup. So the set containing A, B, and C is exactly the same as the set containing C, A, and B. As long as they hold the same stuff, the order you write them in means absolutely nothing. Okay, you know the definition and you know the 2 big rules. Time for a little pop quiz to see if it's all sticking. You ready for this? First question. Take a look at this set A. How many members or elements are in it? Now remember those pro tips we just talked about. Look closely. What's the cardinality here? Okay, let's walk through it. See how the letter C is in there twice? Well, what was rule number 1? No duplicates. So we only count the unique elements, A, C, and R. That gives us our actual set, and that set has a cardinality of 3.
All right, next one. Which of these descriptions results in an empty set? Option A is the set of whole numbers between 1 and 2. Option B is the set of natural numbers between 7 and 9. Take a second. Which one is empty?
The answer is A. Think about it. Are there any whole numbers, like 0, 1, 2, 3, that are strictly bigger than 1 but also smaller than 2? Nope, not a single one. So that collection is empty. But set B, on the other hand, is not empty. The number 8 is a natural number, and it fits perfectly between 7 and 9. So that set actually contains one element, 8. And really, that's the big takeaway here. When you boil it all down, sets are just math's way of being super clear and organized. It's all about taking a messy idea and applying a few simple, strict rules to turn it into a clean, logical group. And that kind of clarity is why sets are the bedrock of everything from database design to the logic that runs our computers. So that leaves us with one last, kind of mind-bending thought. Everything we've looked at today, we could easily count. 3 colors, 3 letters. But what about the set of all counting numbers? That list it goes on forever. It's infinite. So how in the world do you describe a collection that never, ever ends? Well, that's a question for another time.